Let me remind you what we did from the last video. So our goal is to show the following theorem. That basically says if you have a measure on any measurable space, then you can always add in those subsets of the null sets so that you can extend your measure to a complete measure. So that's our goal. And from last lecture, we proved the first lemma, a technical lemma that shows that if you consider the sigma algebra generated by your original sigma algebra B and all the subsets of the null set, then this sigma algebra, you can describe it as all these sets that has the union of two parts, and one is from the sigma algebra you originally have, and the other part is a subset of a null set. So we just show that this is actually the sigma algebra generated by the null subsets of null set and B. In this lecture, we're going to finish the proof of the theorem. So let's go to the proof. All right. So to prove the theorem, we first need to define the measure on this B bar. So on this B bar, let's take a typical element E union F. And I want to define a measure mu bar that extends mu. So I need to tell you what's the value I assign to this set. The idea is E is the part coming from B, so it should have measure mu of B, which come from the original measure mu. And the F part come from a subset of null set, so it's really small. So the mu bar shouldn't see anything in terms of measure on that part. So I just define mu bar in this way. I only measure the E part. Well, this definition may depend on the choice of this E and F. So we need to first of all show that this is actually well defined. So I need to show mu bar is well defined. In other words, I need to show that mu bar is actually independent on the choice of E and F. So suppose I have a set A inside B bar, and suppose I can write it two ways. I can write it as E1 union F1, and I can write it as E2 union F2. So here F1, let's say Fi is contained in some null set, so Ni, where mu of Ni is equal to 0. Well, so by definition, I assign a measure of mu of E1 to A, and I also assign mu of E2 as mu bar of A. So I need to show these two give me the same value. So I need mu of E1 is actually mu of E2. So it's not dependent on my choice of E. So in fact, I want to claim the following. So here is my claim. I want to show that this is equals to mu of E1 intersect E2. Okay, so here's my more ambitious goal. So how do I show this? Well, let's let E to be equals to E1 intersect E2. And one direction is fairly simple. The mu of E is going to be less than equal to mu of E1 and mu of E2. So let's just use EI. So EI being a larger set, E is the intersection of the two, so EI should have a larger measure. All right. So now we need to show the other direction. Let's draw a picture and see. So I have a set A, which can be written as a union of E1 F1 or E2 and F2. So let's draw a picture. Let's see where the F1 may be. So let's say maybe F1 is here, okay? And E1 needs to be somewhere that contains all the complements. So maybe let's call this part E1. So this is E1, and this is F1. So this is F1. All right. So this is one way of dividing it. And there is actually another way of dividing it. Namely, I can do something, maybe F2 is here. So that's F2. It can have some intersection with F1. And it can written as E1, well, F2 union E2. So maybe let's try a different color. So maybe E2 contains everything like that. So that's E2. In any case, the intersection of E1 and E2 is, let's draw a picture. So it contains everything in E1 and E2, and we call it E. So this is E1 intersect E2. Okay. All right. So F1 is contained in some null set N1, and F2 is contained in some other null set N2. All right. So this is the picture. Now let's try to estimate where the E1 can be. Okay. So the E1. So here the E1. Well, let's see what's given the upper bound. Okay. As you can see, well, E1 is actually contained in this entire set. So let's maybe use a different color. So it's contained inside this whole thing here, all right? What does this whole thing consist of? Well, it contains something that's in N1 and N2, so it's certainly contained in N1 union N2. And whatever that's not in N1 or N2, it has to be coming from E1, and it actually also have to come from E2, okay? Because anything that's not in N1 or N2, it means it's not in F1 and it's not in F2, so it has to come from both E1 and E2, so it's also the union of the E1 intersect E2, which is this part basically. All right, so well, we call it E, so this is E union N1 union N2. So by the monotonicity, the mu of E1 is bounded above by the mu of the union of these three sets. And by sigma subadditivity, we know this is bounded above by mu of E plus the mu of N1 plus mu of N2, but N1 and N2 are null sets, so this is bounded above by mu of E. So we just show that E being a subset of E1 is contained, well, it has a smaller measure, but mu of E1 is less than or equal to mu of E, so this proves that mu of E is actually equal to mu of E1, and similarly is equal to mu of E2. All right. So basically now we show that this measure mu bar by defining it as mu of E is actually well defined. Well, now I have a well-defined map on the sigma algebra B bar. I need to show it's actually a measure. So the second part, I need to show that mu bar is a measure. Well, how to show that? I need to check it satisfies all three conditions. Well, mu bar of the empty set is equal to 0. That's fairly clear. Okay, so empty set is inside B, so mu bar of empty set is just mu of the empty set, which is 0. Well, mu bar is positive. Well, you can convince yourself because mu is always non-negative, so mu bar is non-negative. Those two are simple. Well, the harder part, slightly harder part, is I need to show it satisfies the sigma additivity. So let's let elements En union Fn as a typical element. They are inside these B bar. And suppose I have a sequence of them, they are all disjoint. So let's consider what's the mu bar assigned to their union and going from 1 to infinity of this En union Fn. Well, from last time, we saw that this union of two union, you can break it up into the union of E and the union of F. So I can write it as the union of all the Ens and union of the Fns. Okay. Now, the En, that's inside B. And last time we saw the union of Fn, that's going to be contained in the union of the NNs, where each Fn is containing a null set N. So here N goes from 1 to infinity, and where the mu of this union of these NNs is actually equal to 0. It's a null set because each of these N is a null set. So by definition, so here is really by definition of this mu bar, I ignore the subset of null set. So this is by definition the measure of the ENs. Okay, so I'm going from 1 to infinity. And now, because the En union Fn are disjoint, it's clear that En are also disjoint because they're subsets of some disjoint collections. So because they're disjoint and mu is a measure, so we can use the sigma additivity of mu and write it as the infinite sum of mu of En. And then again, by definition, this mu of En is simply mu bar of En union Fn. Okay, so let's see what we got. We get the measure of their union is equal to the sum of the measure, where each of the set is, well, all the collection are disjoint. So this proves the sigma additivity of mu bar. So mu bar is a measure. All right. Now, let's see why mu bar has to extend mu. Well, this is fairly simple. So for every B inside the original sigma algebra B, I can think about B as the element where you take B union the empty set. So this is certainly inside B bar. And our measure mu bar will assign this B union empty set, which is just basically mu bar of B. Well, by definition, well, this is equals to mu of the B part, which is mu of B. So this shows mu restrict to the original sigma algebra. Well, mu bar restricts to the original sigma algebra, recovers mu back. Okay. And fourth one, let's show mu is actually complete. Or mu bar is complete. Well, why is that? Well, to show it's complete, let's go back to the definition. What do I mean by complete? Well, I need to show that for every m inside this sigma algebra B bar, where the mu bar of m is equals to 0, and for every subset, let's say G subset of m, I need to show that G is actually in the B bar. Need G bar, sorry, not G bar, but G is inside B bar. So that's what I need to show. Well, why is that? Let's start from the M. Well, what does it mean by M is in B bar? Well, M in B bar will basically implies M can be written as a union of two things, so E union F, where E comes from B, F comes from a subset of a null set, so F is subset of N, where mu of N is equal to 0. Okay, so this is by definition. So now mu bar of n is equal to 0. Well, this really means what? Well, mu bar of n by definition is equals to mu of E. Okay, so the mu of E union F, mu bar of E union F, ignore the F part. So this implies the mu of E is actually also equal to 0. Now let's look at the set G. Okay, so G is contained in M. And I know that M is no other than E union F. So I can do the following. I can say, well, this is contained in E union N, where mu of E union N, because mu of E and N are both 0, this is equal to 0. So G itself is a subset of a null set. Well, B bar is generated by the original B and all the subset of null set. So G is certainly in B bar. So G is in B bar. So this shows that the mu bar is a complete measure. Well, you can convince yourself this mu bar is really the unique one because, well, if you can write a set as E union F, where F is a subset of null set, then the mu bar, any complete measure of this subset has to give you the mu of E. So there's really a uniqueness really come from the definition. All right, so now we proved this theorem that basically tells us every measure can be made into a complete measure by adding in all the subsets of the null set to the sigma algebra. So let's just give a definition. So I say this x b bar mu bar is just called the completion of the mu of, let's say, x, b, and mu. So here the completion is really twofold. I need to complete the sigma algebra. I need to add in all those subset of null sets and get a bigger sigma algebra. And I also need to extend the measure mu to mu bar.